We will go to transient analysis and to see some examples or some problems which are standard in their nature to understand the concept. Problems are generally two types. Some problems are checking the concept, some problems will help you the concept or make the concept. Today I will be making the concept with illustrative problems or examples or illustrations. So when you are analyzing transient circuits, there are three methods. One is Laplace method, we call it as S domain. Integral differential equation method, we call it as T domain. Inspection method, we call it as direct method. Among these methods, as I told in the previous lecture, time domain method is used for first order systems. If it is a higher order system, you have to go to Laplace transform. But at times, direct method will give you fast and quick answers. So, depending if the direct values are available, better always go by this method. Today you observe me, I will be illustrating all the three methods only for one circuit, and for other circuits I will take only direct method, that means inspection method. For an objective exam, nobody knows, nobody understands which technique you are using. So you can do whichever technique is fast enough, right? Let's go to inspection method, just a review. It basically talks about final value, total response is equal to final value plus initial value minus final value e power minus t by time constant. This is the basic equation. In fact, this is also developed from time domain approach. But that's how this is going to give a short and quick answer. So better understand this and achieve as fast as this one can do the solution. Now I am taking the first problem. The problem is like this. Calculate current response of RL circuit. It is a series RLC circuit. Look at here, switch was kept for a long time, closed at t equal to 0. This arrow says at t equal to 0, this is closed. And we need to calculate this I. To analyze any circuit, we have basically three important things. One is T0 minus, second is circuit at T0 plus, third, any time after 0. When you say T0 minus, you should see how L and C are reacting. T0 plus also you should see how L and C are reacting. For t greater than 0, one important precaution, all the inductors and resistors will present. They are neither open circuit nor short circuit. So please observe this. Why they are neither short circuit nor open circuit? Because you are taking time in general. So in general they are present. If you keep for a long time, they charge fully. When the inductor charges full current, it is short circuit. Capacitor charges full voltage, it's open circuit. So therefore, we are going to see three times, T0 minus, T0 plus and t greater than 0. So please observe one by one. This is here I am talking about T0 minus. What is T0 minus? Just before t equal to 0. Just before means 0 minus, it is talking about current through the circuit is 0. Please observe the circuit. At T0 minus, switch was open. Why? Because switch is closed only at t equal to 0. So this is I. Switch is closed. Then what will happen to inductor? The more important thing today, you need to understand what is happening to inductor and capacitor. That's all. What's happening to inductor when it is alone? What's happening to inductor when it is short? So when it is alone, when it is together with the capacitor, we need to understand. So we will see individual things and also see what is happening for different things. So let us see this inductor basically is not connected to source. When it is not connected to source, could this develop any current? No. No current means zero current. Zero current means open circuit. So inductor is acting as open circuit. That's the point. So when inductor is acting as open circuit, what is the current flowing through this circuit? This is open, this is open. Two open things, automatically zero current. So this is the status at T0 minus. Then T0 plus. One thing we have discussed in the last class, current cannot change instantaneously in an inductor. Whatever the current was there at 0 minus is there at 0 plus. Therefore, in the previous it was 0, now also it is 0. So the overall current is still 0 because this is open circuit. Third, as I said, the third one, we talk about applying, you see, when you say t greater than 0, what will happen? Inductor is present. So we need to apply three methods as I promised. First, I will apply time domain. Look at here, apply KVL, V minus IR minus LdI by dt. That means V is equal to I into R LdI by dt. These are the equations. Now if you solve this equation, you will get I of t as V by R 1 minus e power minus R by L into t. So what I mean is, this V by R you can always say I. So that is the answer we got. When you got this answer, next I am taking what will happen by what you say inspection method. You can observe inspection method, we need two values. We need final value, we need initial value, and then final value. Because look at this, total current response is equal to IF plus II minus IF e power t by tau. So we need to understand final value and initial value. Initial value we already understood, that is II, that was 0. What is the final value? For t equal to infinity, what happens to inductor? Please observe. Look at here. At t is equal to infinity means this inductor is connected to the voltage for a long time. If an inductor is connected to voltage long time, that means it has charged full current. Full current means short circuit. That's why inductor is acting as short. Then what is this current then? Simply Ohm's law, I is equal to V by R. That's why final value is V by R. Initial value, as we discussed, 0. Final value is V by R e power minus t by L. So this is called inspection method. So if you observe, it is taking very fast conclusions. Now same circuit I will take to third type, S domain or Laplace domain people call it. So we already understood t0 minus I is 0, 0 plus also I is 0, t greater than 0, this is the equation, V is equal to IR plus L di by dt. Now what to do? Take Laplace transform, solve for I of s. Then take inverse transform, you can solve for I of t. So V becomes V by S, I of s or L, S into I of s minus I of 0. Now if you solve this one, you will get I of s. Please observe very interesting statement. When you apply Laplace transform, integral differential equation is becoming as algebraic. That's why one of the important application or advantage of Laplace transform or any transform is integrals and differentials will be converted into algebra. And once it comes to algebra, you can solve it and take inverse transform. If you take inverse transform using partial fractions, you will get k1 and k2, and that if you substitute, this you will get, and take inverse transform, I of s becomes 1 e power r by lt. So please observe, in all the three methods you got the same answer. What are the three methods? Time domain method, inspection method, Laplace method. Particularly for first order equations, inspection method is better, or time domain, and if you apply Laplace transform, it is going to be laborious. So for objective questions, I always encourage people to go with inspection method as much as possible. Let's go to how to calculate rise time. This is our second thing to talk. How to, in the same extension of the first problem, we have to see the sketch, The very idea of this problem is to show you how inductor is developing the current. You see here, 0 at the initial, as time is increasing, current is increasing. That's why we made a statement, inductor develops current and hence develops the energy. So this is the sketch for I is equal to I into 1 minus e power e by t by tau. Now look at here. What is the final value? I. For zeta not less than 1, the rise time is defined as 10% to 90%. Please remember, some students are a little bit confused. Sometimes in rise time we are taking 10 to 90%. In some other subjects like control systems, we take 0 to 100%. So let us not say in controls is this and in networks is this. The answer is, it's not the controls or networks. It is a zeta matters. That means damping factor. If the damping factor is less than 1, you go for 0 to 100%. If the damping factor is not less than 1, take to 10 to 90%. Now I am going to substitute. 10 means what? 0.1, T1. 90% means what? You see here? 0.91, 0.9, T2. The difference between T2 and T1 is called rise time. So the word rise time has this meaning, difference. So we will be substituting in the expression and solving for t. Observe here. This is the actual expression. We need to substitute this one, solve for t. When you are substituting t1, you have to substitute t1 and t2. If you subtract from here, you will get 2.2 L by R. So rise time in general 2.2 tau, because L by R is tau here. L by R is tau. Then applications. What is the main application of this? As tau decreases, the rise time decreases. Because just now you saw, let me talk to you back, 2.2 into tau. That means what? As the time constant decrease, rise time decrease. It is rising within less time means what? Fast. So please understand that L by R decreases, rise time decreases, and hence it is fast response. If L by R is 0, this is called ideal switching. If L by R is not 0, it is called practical switching. If L by R is infinity, rise time is infinite. It is taking infinite time. That's called worst switch. So when there is a switching is very bad, it's happening as a good wave shaping. It's a very big challenge. Are you interested in wave shaping or switching? Switch means rising fast. Wave shaping means rising slow. So remember here I have made a very interesting conclusions, keeping PDC in mind, pulse and circuits in mind. That's why I always tell the students, if you are good in transients, you are good in pulse circuits. So I made this here. If rise time is 0, it is rising within no time, ideal switch. but there will be no wave shape. Suddenly jumping is not wave shape. So wave shaping and switching, they are two different dimensions. Let's go to problem 2. We have to calculate I, and because of that I and through that I, we have to estimate voltage. Why I am calculating voltage, Because I want to tell you how the capacitor is slowly developing its voltage, thereby it is storing the energy. Because capacitor stores energy in the form of voltage. So observe this. Again, I'll take 3 steps: T0 minus, T0 plus, T greater than 0. T0 minus, what is happening? Look at here. This is a capacitor. Is the capacitor connected to source? No. Why? Because switch is open. This is not connected here. When this is not connected, what will happen? It could not develop any voltage. No voltage means what? 0 voltage means what? Short circuit. That's why this I have shorted. Short circuit is done. And because of this short, anyway this is open, current has become 0. Let me take the second version, T0 plus. That means switch is closed. Look at here. Switch is closed, but what will happen to the capacitor? Capacitor cannot change its voltage instantaneously. When the capacitor cannot change its voltage instantaneously, it is still acting as short circuit. Therefore, the current is V by R. So this is what happening. That's happening for the current. Now, look at here. As I have told you, I'll directly go to inspection method. There are 3 methods I told you, but I'll directly go to inspection. Only in the problem 1, I have shown 3 methods for you to judge and which method is better. Having understood inspection method is better to go always direct. Come on. If you keep the capacitor for a long time, what will happen? If you keep the capacitor on the supply for a long time, the total voltage will be charged. And when the voltages are equal, no potential difference. When there is no potential difference, what will happen? Current is 0. So that is the meaning. So current is 0, but voltage is total. So final value of the voltage here is supply V. Initial value is 0. Now substitute here. Final value is V. Initial value is 0 minus final e power t by tau. Therefore, the answer is V by R e power t by tau. Now, what are you understanding in this? It is exponentially falling. Okay, voltage. So when you really calculate this, final value minus initial value by this is current here. So current is basically 0, but infinite time is 0. Initially current is rising. Now observe how it is rising. Please understand, this is the current, but when you say voltage, this minus that voltage, this minus this. Final value is V, initial value is 0 minus final value e power this. So this is the voltage we are calculating. And when you really draw this, the rise time of the voltage will also become this. Look at here. The rise time will also come. Please, how I got this expression, do you understand? Put t is equal to 0, e power 0 is 1. 1 minus 1 is 0. That's why voltage is 0, slowly rising. T here, voltage here. Please understand, in the inductor I have drawn for current to show you how the current is slowly increased in inductor, but in the capacitor I am showing voltage to tell you how the voltage across the capacitor is slowly rising. Okay. Now, in this way, okay, again it's the same concept of 10-2. If you calculate, you will get 2.2 into RC. Please look at that 2.2 into RC there. So, there is once again condition. Now, what is the application of this circuit? You look at here RC. If you take RC, what will happen? The voltage across this is slowly developed. When the voltage is developed, transistor is working. That's why, please remember, I have put this as a dotted line. You know why it is a dotted line? It is dotted line because this is not the resistance we connected. This is the resistance coming from the transistor. When the resistance is coming from the transistor, then this will also develop slowly. But I am very happy to tell you one thing. This capacitance is picofarad. If the capacitance is picofarad, what will happen? RC will become less. If RC is less, rise time is less. If rise time is less, it is rising fast. So, rising fast is a very good technique here. Right. Now, let me take you to third problem. The idea of third problem, my choice has become like this. I have shown RL separately, RC separately. Now, I am bringing RLC together. What will happen? Whatever happened with inductor separately, same thing will happen. Whatever capacitor happened separately, the same thing will happen. What I mean is, inductor will act as a open circuit, short circuit at the beginning. As I have been telling in the first lecture, don't mug up open circuit, short circuit. Let us see what I did. Come here with me. T0 minus, please understand, switch is open. Inductor could not develop any current. Why inductor could not develop current? Because switch is open. No current means 0, open circuit. No voltage because capacitor could not develop any voltage. No voltage means what? Short circuit. So, remember only 3 statements. Is that element connected to supply? First point. If it is kept it, how much it is developed? If 0 current, open circuit, 0 voltage, short circuit. This is the 3 words. If you remember, total chapter is through you. You have no problem at all. Right? Now, 0 plus what will happen? Switch is closed. Inductor cannot change its value. Capacitor cannot change. Inductor cannot change current, that means 0 current, open circuit. Capacitor cannot change voltage, that means 0 voltage. Okay? And that is acting as short. Now, if I take for t greater than 0, everybody will come. RLC. So, what is voltage? V by S, R. Differentiation is Ls. Integration is 1 by, this integration 1 by Cs. Differentiation Ls. Then you can take the inverse transform. By applying inverse Laplace transform, we can get the solution in time domain. You know why I have written that? If you get these equations up to here, solution is very simple. Particularly in objective questions, nobody will ask the solution. Because for 2 marks, they can't ask more than that. That's why in GATE exam, nowadays in objective exam, they are asking only obtain the equation. No need to solve. In one exam, he said clearly, obtain S domain equations. So, he is not asking for solution. Only in IES, they will ask the solution. Fourth one, calculate voltage response of RL parallel circuit. Okay. Here, what is the voltage available? I am taking a parallel circuit. What is happening here? At t is equal to 0, this is open. at t is equal to 0, it is open. If it is open, now we have to see one by one. T0 minus, switch was closed. When is it open? Just after switching. That means, is this inductor connected to source? No. Actually, it seems to be connected. Because this is short circuit, it is not connected. Because current is going here and here, nothing came there. That's why there is no current here. No current means open circuit. Then what is the voltage at the output? That is also 0. Why voltage is 0? You may think it is an open circuit, voltage has to be something, but because this is a short circuit, the same short circuit going there. Now T0 plus, what I have been telling, this is inductor, switch was open, inductor cannot change its current instantaneously. When inductor cannot change current, what will happen altogether? Whatever is here will exist. Earlier it was 0, now also 0. But voltage was, earlier it was 0, now it is open circuit, there is a voltage. That voltage is called I into R. So please remember, inductor was open circuit, continues to be open. That's the meaning of this problem. But if you go for t greater than 0 or between 0 to infinity, all elements will present. If all elements will present, okay, here you have to consider inductor also. Then what will happen? If all elements are present, first I will calculate at t equal to infinity what is happening. Why? For my solution, I need initial value, final value. So I want to estimate final value here. For final value, that means inductor is kept on the source for long time. If you keep the inductor for long time, it will take how much current? Full current. Full current means short circuit. If you say full current, short circuit. So final value is 0. Look at here. Final value plus initial value. So final value plus initial value minus final value, if you substitute this way. So this is the answer, IR into e power minus t by tau. That is how we have to get the answer. Now let's go to fifth problem. Fifth problem is basically to say, same idea, but instead of RL, I will be using RC. Now every time 3 steps, T0 minus, T0 plus in general. See there, I took T0 minus. What was the status of switch? Short circuit. If switch is shorted, current is going on here, nothing coming here. That means capacitor could not develop any voltage. No voltage means what? No voltage means basically, simply no voltage means you are taking 0 voltage. So short circuit, that means output voltage is 0. T0 plus, switch is open, but will there be any change in the voltage? No. No change in the voltage, because capacitor cannot change its voltage instantaneously. Understand? So therefore same voltage exists. Now I want final value. If you keep the capacitor for long time, what will happen is final value will, total will come here. What is the total? I here, R here. IR is the total value. So now please go and substitute this thing in the final expression. Final value plus initial value minus final value. Look at here, I am substituting. Final value is IR, initial value is 0, final value. So final value plus initial value minus final value e power t by tau. So that is the expression you have. Now, as a sixth problem, I have chosen all the three elements together just to tell you what is happening. As usual, T is equal to 0 minus. You see that? No current is coming here. So inductor could not take current, open circuit. Capacitor could not develop voltage, short circuit. No current, open, no voltage. Always say these three words. Is the element connected to supply? Yes. If it is connected to supply, how long it is there? How much current is there? Based on that you say open circuit or short circuit. Here for a long time it is closed. So if I go for T0 plus, what will happen? Whatever the current was there cannot change. Whatever the voltage was there cannot change. Earlier 0 current, now also 0 current. Earlier 0 voltage across capacitor, now also 0 voltage. So if you multiply these two, you will get some value. So that you have to substitute as initial value. Then what is final value there? We can't use initial and final values or a direct step because this is having so many components. The best way it is to go for IR, IL, IC. The total current is resistor current plus inductor current plus capacitor current. If you apply V by R, 1 over L integral V dt, C dV by dt is equal to I. You see that? This is the expression. Then if you take Laplace, I of s 1 by R plus Ls plus 1 by Cs. Okay. So when you really go for this Laplace transform, you can always solve that equation. Okay. And that is for the expression that you have. Then you look at here, what is V of s? Then you can always solve this method. So as I said, we will give only equations. We will not give any, we will not solve the solutions, we only give equations. Then seventh problem. Initial and final values must be calculated. Take for example, this is inductor, this is capacitor. What is initial value? It is not connected, that's why 0. If you keep it for a long time, what will happen to inductor? If you keep it for a long time, inductor will fully charged. That means answer is V by R. Similarly, let me take you for capacitor. In capacitor we take voltages. In a inductor, if you put this capacitor, it will charge fully. That's called final value. Final value is total V. Initial value how much? If you connect to the supply, or there is a voltage. If it is not connected, it cannot develop. That's why 0. This is called initial value, final value. Like this, we can calculate from the circuit, and at the same time, you can also calculate from the expression V by R T. You substitute T is equal to 0. This will become 1. 1 minus 1 is 0. You substitute T is equal to infinity. E power minus infinity is 0. So 1 minus 0. So this is here. So please understand, I am also giving 3 approaches for calculating initial values and final values. First approach is time domain. So take the expression, substitute T0, initial value comes. Substitute T infinity, final value comes. Now next I am going to take S domain. When you take S domain, very simple. You have to say initial value theorem, final value theorem. Initial value theorem is very simple. When you talk about initial value theorem, it is S into I of S. Final value theorem, S tends to, when T tends to 0, S tends to infinity. When final value, S tends to 0. So T is infinity, S is 0. You will get the same answers. Even in the capacitor also, you will get the same answers. Look at the same answers, how they are following this. Okay. Then RLC circuit. RL circuit also you can substitute what is final value, what is initial value, because limit s tends to infinity, s into I of s is giving initial value. Then final value means s tends to infinity, s into I of s. Substitute there. Substitute. When you substitute, the final value is basically the maximum voltage is coming there. Now I have named it as a physical method. Look at the word physical method. The word physical method means RLC circuit is here. When you say RLC circuit, you have physically, look at here, RL. You have, when you say R, put open circuit, then how much current is there? 0. Keep it for a long time. When you keep it for a long time, how much current is there? Full current, that means V by R. So initial value is 0, final value is infinity. Similarly, when you talk about RC circuit, how is this? This is not connected. Not connected means 0 voltage. 0 voltage. If you keep it for a long time, total voltage comes. So initial and final value theorems you can also get from physical circuit. So therefore, I am giving you 3 approaches. To calculate initial value, final values, you can say using the time domain approach, using the S domain approach, and finally using inspection or physical diagrams you can always get. So which will be the best suitable for? The best suitable is physical circuit. Suppose you are going for time domain, you need to get the time domain equation. If you are going for S domain, you need to get the S domain equation. If you are going for physical domain, you need physical equation. That's why always go physical method, no equations are involved. Just draw it. Is it connected? It draws current. It's not connected? No current. No current means open circuit. Drawing current fully means short circuit. So physical approach is always better. So now I am concluding 2 sentences. If you are analyzing, as much as possible go with inspection method or direct method using initial value, final value. If you want initial and final value also, physically. Therefore, what is my conclusion? Calculate the initial value, final values from the circuit and substitute them in the direct method. You will get some questions on initial and final values, some questions on calculating the actual expression. Both ways, both are physical things. So use physically, use the diagrams physically, and you calculate, you will get the overall expression. So this is about illustrating basic equations of RLC circuits in serial, RL circuits in parallel, and their respective initial and final values. Okay.